question from Thomas Pfaff, who's also with Vienna. That's one of the few, I think, who did not do particle physics.
Yeah.
Environmental engineering. And we'll talk about advanced efforts.
Okay. Thank you very much. One question beforehand: who managed to get to install the environment we would use for this? So that's a few hands no, and apparently only 3 to 4. So I intended this to be a really hands-on exercise. You can try, if you have Conda active, to just try Conda install PyTables and NetCDF4 and pandas. And if you're lucky, the network will hold and give you a working installation. Then you can either fire up IPython or the notebook, whatever you have installed. Everything should, all that should work. For the beginning, I'll stick with doing live coding. If you say this is going too slow, this is boring, I can switch to the Jean Pütz version, which I have already prepared. So just raise your hand and give me a call if necessary. So starting the time. No. All right. So my name is Thomas Pfaff. My job description is right now is data scientist at Blue Yonder. Before that, I might have called myself radar scientist. In my PhD thesis, I worked with weather radar. And whenever you deal with meteorological measurements, you also have to deal with lots of data. That's where I came in contact with the formats HDF5 and NetCDF. And today I would like to present the ins and outs of these data formats as we can use them in Python. Starting right away with HDF5. That format was invented basically by, it basically is used most prominently by NASA, saving all the data that they get from their Earth observing satellites. And basically you can download many products by HDF5 files directly. How do you create one of those files? It's fairly easy. I hope this will work because, First thing you have to do is to import PyTables. And this contrast sucks a little bit. Can you see? Not really. Me neither. So I will have to talk myself through that. PyTables, and because I will produce a little bit of NumPy stuff, I import NumPy as NP.
Can you change the font?
Can I change the font? I have.
Invert the colors. There's like this combination of Mac that inverts the colors. You know it? Or just make it.
If I had a Mac, I would try, but
I'm so sorry that I thought you did.
I'm very sorry. For the next talk, I will get one.
I thought you did have a Mac.
No. I'm really sorry. Okay, so import tables, import NumPy as NP. And then it becomes fairly easy. You say I want to have a variable, and I call tables.open_file with a file name, data.h5. Basically like the Python open command, and then there's the file mode, which can be write, read, R+ for read and write, A for append, as you know it from standard Python. And this basically creates your file. Nothing in there, but you have a handle you can write to. Now how to populate that? As the name goes, PyTables first focused on using the HDF feature of adding inhomogeneous data. So you can add something like a pandas data frame as a table or a record array to an HDF file. Why is it called HDF? HDF is short for hierarchical data format. So in these files, you can have hierarchies of data. And they model that by using a Unix-ish like path system. So you have groups, which would relate to Unix folders. And then you have the data sets that would be represented in a file system as files. And now we're going to fill our file and say we want to have a people group, which is our file, create group. Then we have to tell PyTables or the HDF file where we want to have that group, so on the root level, and we want to call it people. We can also ignore the return value and just say hf.create create group also on the root level, and we call that one data. So we have a file called data.h5. In that we have a folder called people and one called data. And if I fire that, the reference to that data folder is lost. If I want to recover it, I say data is hf.get node, and where would that node live and how it is called. And this way I get a reference to my data group back. So now we have two folders in our data file. Now let's fill it with data, with actual data. As I said, one of the data sets you can put in there is a table. We will talk about the other formats later. So we have set up a variable, saying people equals hf.create table. We need a little bit more space. So we start, where do we want to have it? We can use a string, but we can also use a reference to one of these groups. We still need to give it a name. Let's be creative and call it people. And then we need to give it a description. And the easiest way is to just give a NumPy type. And you know how that goes. It's a list of tuples stating the name of that particular column. And we say the name is usually a string of a certain length. And we might have an age, which is a 2-byte integer. And we might have height, which could be a 32-bit float. Once we've done that, I need to get the brackets right. We also can give that a title. So adding some metadata, say some tutorial participants. And if I got the brackets right, I will see in a moment. Apparently, yes. So now we created a data object. Oh, that's a bit more to type. So adding to this table is fairly simple. So the basic message that I want to get across, even though these data formats, I would not want to look into them, and I would not want to program anything that accesses them by myself. The interfaces that the PyTables guys and the NetCDF guys have written make it very, very easy to access these files, to work with them like in-memory arrays or in-memory data, append to them without having to wonder or to care how this stuff finds its way to disk. So, getting some people data in. People.append, And then we add a list of tuples. So clearly, I'm a participant of this. I will even tell you my age and my size. Anything else volunteering to give his or hers? Anyone? Jeffrey. Like this? GEO. Like this? Okay, so you can lie about your age. 39. 195. All right, so 2 is enough. Anyone else? No. For the sake of speed, I append them and then I want to get them back. And one of the big advantages of PyTables compared to other libraries is that it exposes the object hierarchy in the file as attributes of the object. So you can say HF root, that's the root element. We have the group people, and we have the group people, and we even get tab completion here. And then we can retrieve with standard slicing now all elements of our table. So that should be two things. Let's see if that works. So we have, what we get as return is a NumPy record array with these 2 entries. You see, that's an integer, that's a float converted to this strange format. And then you have these data types. So that's the way to access tables, and they have a fairly sophisticated means to access these tables, to do filters on them, either directly using Python's list comprehensions or in core, so a little bit faster. I don't want to talk about those, regrettably. I would like to go more into the homogeneous arrays, which I find more fascinating. But before we go there, I'd like to show you how to add additional metadata to those values. I think most of you know the dilemma. You get a CSV file and you have lots of data there, but you have no information where they come from. Well, somebody sends a document where everything is explained, every column is explained, and when it was taken and by whom and where it came from. And then somebody asks you for data and you give them the CSV file and you forget about the document. You explain it to them during a telephone interview, he writes it down somewhere and he passes the data on, and sometimes there's just a CSV file, nobody knows what's in there. With HDF files, you can add the metadata directly to the data set, and there's no way you're going to lose that again. So, and adding attributes is as easy as adding the data itself. Wherever you have, like for example, our people group, it has a special attribute called v-attrs. And there you can just add new attributes, like this one, right? It doesn't exist yet, but you can make it exist. And now if you could look at that, these are a few attributes that PyTable sets for itself to make make sense of the data it sees, to be more efficient and better able to convert that thing in something very Pythonic. But here's your description attribute. And let's get saved to the file, and whenever you pass the data set, you pass the description with it. This was done to a folder, so to say, so you can document a folder. But you can also document a data set itself. Guess how you do that? You say people. There you can use something that actually sounds like attributes. And then you say, for example, date created, and that is 2015, 30, May 30. And then we can look at people address. So as a data set, Python's PyTable saves that it's a table, that it has names, name, age, and height, and the field values, and so on. You have the title that you gave when instantiating the table itself, and you have the additional version information about the date created. With PyTables, you could even save a datetime object. But if you want to use that HDF file with another program or library, that might have difficulties interpreting whatever PyTable saves there. So if you want to be sure, use standard data types, strings, floats, and so on. But if you're sure that you will only work with PyTables and maybe another Pythonic Python package using that file, you may as well save any kind of object there. So. Yeah. Well, here it's more like it's a little bit more speaking. If you look here, it references the same attribute. So you could also say v-address if you want to stay consistent. All right. So one last thing. If you lost all references, you still can get to the attributes. You have the function hget node attribute, and you even don't have to worry about the v-address. You just say people, and then access date created. So this makes it also feasible to access these attributes if you don't know during computation time or during coding time how the attribute will be named, or when reading it from a configuration file. All right, and now the interesting stuff, working with arrays of homogeneous data. The HDF file format provides 4 different kinds of arrays, like NumPy arrays. There's the contiguous array that reserves the contiguous amount of memory in the file, immediately reserves that on disk, and lets you very efficiently write and read from that chunk. The second one, which is the most interesting part, is the chunked arrays, where the whole dimensionality of the array is subdivided into chunks, something similar to what we heard last morning with Dask array, where you divide your data into chunks. That enables you to first compress those, making the file size much smaller, and only save those chunks where actually data is in. So you can define a huge array, but as long as you don't write data to it, your file stays small. And if you have a very sparse system, that might be an advantage. You have an enlargeable arrays. That is the speciality of PyTables. It provides you with one enlargeable dimension. HDF5 actually provides you with unlimited enlargeable dimensions. You just say, this is going to be a 3-dimensional array, but I don't know what size those 3 dimensions are. Something that NumPy can't do, but HDF can. And then you can grow this array as your data comes in. And finally, there are the variable length arrays, that are arrays that are not limited to a certain size. So in the following, I want to talk about the chunked arrays, how to create one. So you say, for example, CA is a hf.create C array. Then you have to tell PyTables where that lives. We put it into data folder. We may call it C array. we need to give it the data type, and here PyTables provides you with so-called atoms. I'll use the float 32 atom. Oh, sorry. And in that atom, you can, for example, give the default value. Let's say we use npnam. We need to give it a shape. Let's say 100 by 100 by 100. And I always make it a typo here. And that's basically it. Chunked array, 1,000,000 entries. If you take a look at your file system, the file has grown because we added the table data to it, but it has not grown to the size of 4 megabytes.
Why you have to provide this special atom site? Some special type of HDF?
Well, you would have to ask the PyTables developers that, why they did it.
So you cannot just put the usual Python.
No, regrettably not. The advantage is, I think maybe they wanted to do that because using an NumPy type, you can't say what's the default's going to be. So because now you have defined the array, you can access it. If you haven't written data there, it will return npnum. Or it would return -34 if you told it so. Yeah.
So for me, it's still 0 byte. Do I first need to flush it?
Yeah, you can flush it if you want to see it. HF.flush forces it to write to disk. All right, so, sorry, where's my pointer? Here. Let's take a look at the chunk shape of this one. Yeah, tells me I can't create something that I have already created. And we do that like this. If you don't give a chunk shape yourself, you can do that. We will do that in a moment. PyTables or HDF guesses what a good layout would be. So in here it says, well, maybe you want to save images along a time dimension. So there will be one. The chunk will be like a flat cut from that three-dimensional cube. That's pretty much what I wanted. To show you what the results are of a different chunk shape, I'll define another array. Oh boy. That's flying a little bit by wire. Okay, we need to give that one a new name. First as a variable. Second as, and then say chunk shape. Let's say 10 by 10 by 10. That might be a chunk shape more suitable if you are not sure if you always will look at the images or if you want to have time series analysis as well on that kind of data. If you're sure that you want to do time series analysis, you choose a chunk shape so that it reads along the first time axis or the time axis that you define. Okay, so let's look what that chunked array looks like. Hey, where are you? Oh my God. Here's the node attributes. Ah. So slicing a little bit, the first two dimensions, the first two elements, and then to the fifth element. You see, I haven't put anything in there, so I get the default value back. But at least I get something defined back. Now let's fill this. Create some data that is, for example, NumPy random numbers, 100. And then a bit of fancy indexing. Non plus just in case that you wonder what all this dark magic is that I'm doing. Or are you familiar with this kind of stuff? All the better. So I created 100 random numbers, put them in the first dimension, and then I put 100 A-range numbers and added them to the random numbers over that second dimension. So here you have the random numbers. Here it's incremented by 1, here by 2, here by 3. So this way down is compression levels should be fairly bad, and the other way around it should be better. So we have a quite well compressible random number field. And now we want to fill that into our file. So defining a function fill array that takes an array. It doesn't care about whether it's a NumPy array or something else. Okay. Thank you. Colon and say for I in range array dot shape 0. Array I comma. So we made fairly a lot of assumptions here, but it's just to make the point. And now we can see what happens. If we time access to that, we say time it fill array. We pass in our chunked array, and we pass in the data. And we hit go, and we wait a little bit, and we get 100 loops, and the best one is 6 milliseconds to fill our 1 megabyte field. If we try that with the other array, it's roughly a factor of 4 slower, because our array was aligned in the same way that the chunks were. It was easy to do that in simple and very few operations. If our chunk size is a little bit off what we insert, then we have to pay the price that the library has to pull in many chunks, fill the data, and then pull all those chunks back. So there's a risk and a chance. If you do it wrong, or if somebody says, well, this HDF5 stuff is so horribly slow, I don't want to use it anymore, maybe ask him, have you chosen the right chunk size for your problem?
Is there a way to change the chunk size?
No. No. You have to decide beforehand.
unless you load everything in memory and write it to another table.
That would be the option. You create a new array with the right chunk size, and then you make a big copy operation. Yeah. And now that we have filled the array, we can check if the data is really there. We say HF, let's make it interactive, .root, .data, .carray. I want the real one, and the same as before. And there's our data, right? As before, the random numbers in the first dimension and the additions in the second dimension. And this is a three-dimensional array as we expected it. So next, let's have a look at compression. As I said before, chunking enables you to compress your stuff. So let's say, for example, du minus h of data.h5. That's 7.6 megabytes. Right? We have 1 million elements of 4-byte floats. That's 4 megabytes for one array, and we fill 2 arrays. That's 8 megabytes. If you use a non-human readable size, it gets even closer to the 8 million. So how do we add compression? Actually, that's fairly simple. Well, first we open a new file. Call it compressed HDF5 file 1. Say tables, open, file, compressed data.h. Well, and it's compressed data 1.h5. And we open that for writing as well. And next we say compressed chunked array number 1 equals HFC1 create C array. On the root level, call it compressed. Use the float atom. Forgot tables. Not giving any default now. The shape, let's break it. Shape should be 100 by 100 by 100, as before. And now, because we know that the chunk shape is going to be good for us, we say we add a filter. There's the filters class, where we can say we want a compression level of 1, for example. You have a few other options there, whether you want to use a shuffle filter. Who joined Valentin's talk knows what the shuffle filter does. It reorganizes the bytes so that the compression can be more effective. There's a checksum filter that you can activate that will complain if the data in your file has been corrupted. And you can also, with PyTables, you can choose what kind of compression library you want to use. Here we use the standard, that's going to be zlib. And now we create this array. So if we look at how large it is, oh, giving away a few things. Forgot to delete the data. So this is what we created. Right now we haven't written anything there and we haven't flushed. So that's 0. And now we fill that stuff. CC array 1 and our data. So ideal chunk size, factor 4 slower due to the compression. But if we look at the file size now, this is 490K as opposed to 8 megabytes. Of course, that's a special example, but you can at least expect a factor of 2 or something, depending on your data and depending on your chunk size, to get improvements without having to care, right? We still only had access using the NumPy-ish interface. So choosing a different compressor, for example, can give back a little bit of speed. And here I wanted to show you what that may make. And what I'm adding here is you can add the filters keyword to any level of your hierarchy. So you can add it to a data set, as we did before. We can add it to a folder. Then all data sets below that will use that filter unless you give explicitly another one. Or you can also add it to the file itself. And then, unless you say anything else, every data set will be applied with this filter. And for example, the comp lib, we should say it's blosk. Adding a new array.
Short question.
Yeah.
Is there a difference between the create_C array and create capital C array? If you do a completion, it gives you both.
Initially, PyTables was designed with these camel case letters. And with the new release, they decided to make it more PEP8 compatible. So, and for time being, they use both. But encourage people to use the new version. So there's one missing. And then we have to say again, time it and fill the array. and our data. And now we're already back to close to where we were uncompressed, and looking at our disk usage now. At least a factor of 2. You could have used comp level 4 and get back to that size and still be reasonably fast. One caveat here: the standard HDF5 library only supports zlib. So if you want to use it outside PyTables, better stick to the standard. BLOSC won't be available for all HDF readers out there. There are tools like the HDF viewer provided by the HDF group, or VI tables, and so on. And there's no guarantee that they have these compression libraries available, that they were linked with those. So if you want to make sure that somebody else uses it, can use it, stick with the zlib. Who of you has been using the HDF saving feature of Pandas? 1, 2, 3, 4. Have you looked into the file that Pandas creates? You interested in how it looks like? Or actually, you can see for yourself. I think we have enough time. Let's look how these interactions with Pandas look like. So let's import Pandas as PD. And say we want to have 10,000 data points, and we create a data frame. That consists of 2 columns, the one we call A, and say that's n random numbers. And the other one we call B. Guess what? N random numbers. And now, let's say df to HDF. Let's call that data frame H5. And the to HDF we say data frame, it's the group. It should go to the group data frame. And we can say df to CSV, for example. Data frame.csv. That doesn't need anything else. Write it to disk. And now let's see how it looks like. HDF's tables, open file, data frame.h5. Now we're open for reading, which we can state. And we can have a look. If you just call, or if you just, this is the return value of tables open file. So what do we see? Pandas produces a non-compressed file without any title. It adds a group data frame, and in that group it adds several data sets. There's something about axis 0. That's the row labels. Then there's, no, that's array 2, that's the column labels. So it's a string atom. Because our column names A and B fit into something of size 1, it saves it like this. As axis 1, that's an array of 10,000 elements length. Integer, that's the index. And then it says I have items in block 0 and I have item values in block 0. And here it stores its data. And funnily, it stores all columns of the same type in one block. So now we added 2 floating point columns, so they go in one block. If we had added a string column, we would have 2 blocks, one for the floating points and one for the string. Okay, now I want to close this again. Now I want to know how much faster we can read that stuff. PD data frame dot from CSV. That took 36 milliseconds. And here we also have to give the group. So you could save more than one data frame into one HDF file. That's slightly faster. It's a factor of 10. So those who did save it most probably saved it for that reason. The other ones can do that now too. And as for size, it even has a slight advantage. That's not always true, but in here it makes a perfect case.
There's a way to get, I recall, to get pandas to compress the H5 file as well. Okay?
I would guess so. I'm not sure. I haven't.
recall seeing like somewhere in the API. It's
Okay.
either in the call when you do HDF or something. You can tell it to compress it.
Yeah, I would guess either they have provided a keyword,
Yeah.
or they would accept an HDF object comp level. So, there you go. So even less space. Right. I'm in the wrong browser window. So with that, I would conclude the HDF5 part and would move on to NetCDF4. NetCDF4, yeah.
Before you move on, could you
Yeah.
comment shortly on the difference between PyTables and H5Py?
Okay. The question is, what are the differences between PyTables and H5Py? I wanted to do that in the end of the talk, but I can do it here as well. Basically, PyTables provides a more interactive interface with the exposure of the data sets as attributes. Makes it much faster to write all those things. H5Py uses the similar interface to what NetCDF is using with mapping all these things to dictionary objects. That's one thing. When I used PyTables, admittedly a couple of years ago, PyTables was much more mature. H5Py had a few performance problems in several cases. On the other hand, H5Py makes a much better does a better job at, or it intends to bring as much of the HDF libraries functionality to Python. So there are a few things that PyTables just doesn't do. For example, the extendable array has only one unlimited dimension, and then you can only append step by step. While with H5Py you can define unlimited dimensions, and you can resize an array by saying, well, I had 10 by 10 and now I want to have it 100 by 100, and so you get immediately the new space and can write more efficiently than just appending step by step. That would be the main features for me for H5Py. When I checked before the talk, they have now implemented the parallel feature of HDF5, which would enable you to write to the same file from different processes, something that you cannot do with PyTables yet. So I think H5Py goes more into the direction, make it as feature complete as possible, while PyTables is more for the ease of use and the interactivity, and maybe a bit more performant than the other one. All right.
One more question. What about text or variable length strings? Would they have
Variable length strings,
huge file?
I'm not entirely sure.
Okay.
You would have to read the documentation, which is pretty good, as most Python documentations are. Okay, NetCDF4. Under the hood, actually, NetCDF4 uses the HDF5 format. But it adds a little bit on top of that, which makes some things easier, some things less easy or even impossible. And it forces you a little bit more to document your data. We'll see that, how that works in a minute. So, how to create an NetCDF file? Well, first you have to import NetCDF4, we say SNC. And then we can say NC dataset. Basically the same syntax as open and OpenFile had. Opening it for writing, and this way we create a new file. Now the first thing as NetCDF differs. NetCDF also has groups and datasets, so it mirrors the hierarchy of HDF. But it forces you to define so-called dimensions. In HDF, we could say, create me a C array of 100 by 100 by 100. Effectively, we will do the same in NetCDF, but we have to give a name to each of these dimensions. It's mainly used in climate research, and there, these array dimensions have a physical meaning. They're mostly X, Y, latitude, longitude, time, ensemble member, and so on. And so NetCDF forces you to create that. And therefore, we will have to do that too. Doing ds.create dimension. We need to give it a name. And we start out with time. And we say none. And that means this dimension is going to be unlimited. Let's create another dimension. Call it X, and say this is going to be arbitrarily chosen 131 elements. Then we create another dimension. And guess how we call it? Going to be the same size. And what you see here is the return value of the last statement. It returns the reference to that dimension if you need it further into your code. Oh, that was the adding dimensions part. Now there's adding variables. Variables are the data sets of NetCDF. And it's good practice to create a variable of the same name for each dimension that you have. Therefore, you can say, for example, my time dimension, each element of my array in this belongs to that certain time. Or the x dimension gives you, or the latitude, longitude dimension gives you the latitude and longitude of this grid row or column. And if you do that, there are tools like grads that can read your file and immediately work with it and display the data and run all kinds of fancy analysis with that. If you don't do it, you don't need to, but then you can't use these advanced features. What we now will do, we just create a data variable. Call it data. Here we can give a NumPy data type to determine the type. Here say NumPy float. And then we need to give the dimensions. We say, for example, this should be 3-dimensional file, time, y, and x coordinate. That will be a typical format for example, radar images. Several images stacked up on each other. So now you see here, it's an NetCDF4 variable with these dimensions. The unlimited dimensions are time. So the current shape is 0 and 131 and 131 for x and y. You can give a fill value if you want as a keyword to the create variable function. So, nice thing about NetCDF, variables grow dynamically. If you assign to it, it grows to accommodate for what you assign. So we can say, first we can say, what is the... okay. Let's create a variable. And call it time. So what I said before. And I have to reuse this. Let's say all variables are stored in an attribute variables and are accessed in a dictionary fashion. And implement the NumPy interface. So the variable time depends on the dimension time that is currently 0. Let's look what the variable data looks like. We saw that already. 0, 131, 131. Now let's add some data. For example, let's say these variables. Time element 0 equals 100. That works. And if you go back and ask for the shape of the variable time that you just added to, of course it has shape 1. But because that is depending on the dimension time, if that dimension has increased, it has increased in all other variables that it belongs to. So also the variable data is now increased by 1. And if you add something weird to let's first look at the data. Nothing in there so far. And if we go to, for example, element 5, that might break. Yeah, not defined. So in here, we can access because it has the right shape. We haven't entered anything. So NetCDF returns a masked array of all missing values. That's different from HDF. That would return the float array with the fill value at missing data points. NetCDF presents you the additional information. There you have entered data, and there you have not. If you pass a masked array, it will honor that and produce missing values accordingly. So now we add a little bit data to this one. No, I don't want to save screenshot. Data. Let's add that to element number 5 and all others. Random numbers. Damn it. Thanks. That works. So, what do you guess? Of course, even though we didn't touch it, the dimension has changed, so the shape of this one changes. And of course here, because we added data, we had to increase dimension. Nice feature for interactive work. Bit dangerous if you do your indexing wrong. I did so preparing that talk. Can quickly fill your hard disk. But basically, you don't need to care about resizing, which you have to in HDF5. So, are we already there? Yeah. Because in climate modeling, time is so important, NetCDF provides you with a few features that HDF doesn't provide, or at least this NetCDF4 library in Python provides them to convert indices to time back and forth. To do so, if you have a time variable, you add attributes the same way you do with HDF. There's a convention that you, for example, add an attribute units. You can do that for any other variable, but for a time variable, it becomes very important, because if you do it like saying, and I will need that more often now, if you say time.units equals a string like hours since 2015 0530 0000 00.0, and you add an attribute like calendar. There are a few calendars that you can use. There's a standard calendar, there's a Gregorian calendar. Very interesting read about calendars. You can have a Julian calendar that's good until 1512 or something, October. And then there's the Gregorian calendar that is good after that, or 15 days after that. There's a proleptic Gregorian that is good for everything, except that it ignores the Julian part in before 1512. and so on. At least if you give something like that, the documentation gives you what calendars you can give here. Then you have a few nice conversion routines at hand. Say, for example, I want to calculate a running number based on this calendar information for a certain date. And so that you can calculate it easily, we say, for example, date to num, and we add a date time object of 2015, 5:30, 12. What's the time now? Roughly 16 o'clock. And if you give that the units and the calendar, of course you can just give the strings, but if you have an unknown and NetCDF file, you don't need to care. But if you give the units and the calendar, then it will calculate the number of hours since this time as a floating point variable. And of course there's the way back as well, which is called num to date. Say, for example, 18.3. And then time.units, time.calendar. And you get a datetime object back. So in many NetCDF files, the time variable belonging to the time dimension is filled with floats like this. And with these two functions, you can convert the floats to a datetime object, which is far more readable. Or if you create one, you can use the inverse function to populate one of these time variables. In addition, there's a function called date to index, where you pass in, well, let's do it. Let's say you have a time, the first 10 elements we fill with an A range. Ten times 3. And then we say NC date to index of a datetime object 2015 5:30 1500. And there you can just give the variable time. Then it will calculate at what index in your variable you will find that particular time.
And then round to the closest index.
You can configure that. By default, it raises an error if it doesn't find it exactly. And you have the options, the earlier date, the later date, or the closest date. And the standard is the exact match. Yeah, that was to show you how the time variable looks like now. Right, so 0, 1, 2, 3, 4, 5. That's 15 o'clock. that we asked for. So that's very nice if you have to work with time series a lot. There's no thinking about no index calculations by yourself, just using these functions. The next cool thing about NetCDF that it allows you, H5Py might allow you to, it's basically the HDF library enables it, is multi-file access. So as an example, I have downloaded from the American National Weather Service a data set of radar data. That's the radar in Oklahoma, the year 2005. And I created those 12-month data files. But that's fairly often the case that you get data files for a certain period of time because the whole thing would be just too large. It's just much easier to manage in smaller chunks. And now the multi-file interface allows you to treat all those files as one large file without having to care. And doing that is very easy. There's an MF dataset where you just pass basically a wildcard expression, and it looks for all those files and pulls them together. Now, what can you do with that? Of course, you can see what variables are in there. So apparently there's a precip array _0 variable that contains our data. There's x and y coordinate, and there's a time coordinate, and along that, it looks, when it does that multi-file concatenation, first it gets the ones in sorted order, then it looks for the first unlimited dimension it finds, and then it concatenates all the arrays along that dimension. It's read-only, unfortunately, so you can only do read operations there.
Just don't want to interrupt, but we have 5 more minutes.
5 more minutes?
We started 20 minutes late. But...
Okay. My watch says I'm 1:11, so I have 20 more minutes, but it's okay. I show you the cool stuff and then we stop it there. So let's look at the time variable. For example, what are the units? I made those up. So it starts at 2005-11. The point, what I want to make is, who remembers what happened in 2005 in Oklahoma? Pardon? Maybe there was a bombing. Would you see that on a weather radar?
No, okay, no. I think that was earlier. Anyway, I have no idea.
Okay. As the year of Hurricane Katrina. That one made its landfall, according to Wikipedia, on August 29. And so you would, of course, you can open just the August data file. But now that we have the multi-file data set, we can, for example, look at the index. Let's say 28, 5 o'clock in the evening. There's a missing in 2005, yeah. Okay, and what is that index? Actually, I don't care what that index is. I got this from Jake Vanderplas, an animation example. And what I'm doing now is I'm accessing the variable principal array based on this index for a couple of frames. So I have 350 frames here, and it starts with frame 0, and it loads the data from the file, and it walks on. And I hope that the infrastructure here doesn't kill me. No, there you are. Say hello to Katrina approaching the radar. Say hello to Katrina's eye. A few data sets are missing. And there she goes. And while this will repeat endlessly, so that's what you can do with a multi-file dataset without caring whether you walk across a month border or your border of your dataset. To make that point a bit more pressing, I can say _0, and I can retrieve all data for a certain point. Damn. Now I'm truly broken. There, I did it again. This is code. For example, 8060. I don't know what there is, but I can calculate the mean over it. All the data over all the files, without having to care. Of course, this pulls that stuff into memory, so you can't pull the whole thing into, well, you can try. If your computer is large enough, you can try. But whenever you do slicing operation, it pulls that slice into memory. But at least you don't need to worry about the other stuff. So with this, I would come to a close. My summary, a bit I did before. So PyTables is very mature, very efficient in my opinion. It's great for interactive work. It's very flexible by virtue of the flexibility of the HDF5. But it doesn't implement all features that the library implements. Their H5Py does a much better job. NetCDF has a smaller API, smaller set of things that you can do, but that it does well. It puts a bit more restrictions on what you have to do in addition to just defining your data set, but it enforces more metadata, which is not a bad thing by itself. It has very convenient time handling and multi-file interface, and therefore is also practical beyond that it's just another layer over HDF5. You can Google them yourself. Big thank you to Damien Avila for doing that RISE presentation stuff, where you can put notebooks into something very useful, I think, very presentable. And if we have questions. If not, thank you for your attention. Hope you enjoy working with those data formats. Thanks.